Speaking.
Okay. So am I audible? Someone can respond. Okay. So hello everyone. I am Prakash Joshi, first year PhD student here at IISER Mohali, working in the area of algebraic geometry with Dr. Vaibhav Vaish. So I will be TA for this course, Rings and Fields, Introduction to Rings and Fields. So this will be our first interaction session. So I hope that you all will participate in this interaction session and make it will be a good interaction session because it will not be a teaching session. So it will be an interaction session. I will try to solve your doubts and we will discuss here. Okay. So I will turn off my video now. So let's start. I will share my screen. Can you see my screen?
Yes.
Okay. So let's start with your doubts. So someone have some doubts. I cannot go again and again Zoom meeting. You can unmute yourself and can talk right now. Okay. So let me see participant list. So Aniket Agrawal, do you have any doubt?
Yes.
So what is your doubt?
No particular doubt till now.
Okay.
At least, yeah, like methods I know. Some most of the questions I am able to tackle using those methods. At my level, at least.
Okay. I cannot take everyone. I cannot tell everyone's name and can ask. Please unmute yourself and talk. What is your doubt? Because it is interaction session. So, Hardeep, do you have any doubt? Okay. No one is responding. So let's start. So since your first assignment submission last date is 8th February, so I cannot solve that assignment this. So I will solve that in next tutorial session. So today we will discuss something else. Okay. So let's start. This one. Let me select my pen from here. Okay. So basically, this is rings and fields. So first part will be rings, right? So let's start. You all did definition of ring. So someone can respond. What is a ring? Definition of a ring. Then I will try to explain why we are going in such a way. First group, first set, then group, then ring. Let's start something basic. So someone can someone tell me definition of a ring because it is the interaction session. So I hope that all you will participate. Okay. No one want to talk with me?
Yeah. So with respect to addition, it's an yeah. Aniket speaking. Yeah. So with respect to addition, it's an abelian group. Then it also has this distributive properties like a times b plus c is a b plus ac and so on. Also, also it needn't have a multiplicative identity. Yeah, but it respects certain things like
Yeah,
yeah, it needed be commutative in multiplication.
yeah. Correct. So
Yeah.
basically, but I see your notes, and there the structure assumes for this course that he will work with commutative ring with unity, right? So as far as we will do this course, we let's assume that we will always, yeah, basic definition of, let me tell you definition of a ring, right? So what is a ring? Suppose R is a non-empty set. R does not equals to 5 is a non-empty set. So then when what is a ring? It will have a two binary operation. It will have a two binary operation, right? Two binary operation, right? What is this? This will be R cross R to R. What is that? One is plus and one is dot. Sorry. So let me cut out this. I don't have eraser here. So let me try to crisscross. So what is this? So A plus B, A comma B goes to A plus B. And second one is A comma B goes to A dot. These are two binary operations. And then we have some condition like this first one. This first one is that R plus should abelian group, right? Is abelian group. And the second one is R dot semi group. So I hope that you guys done group theory course. So can someone tell me what is the definition of abelian group? Please unmute yourself. Otherwise, I don't know how much you are learning from this. So please unmute.
Yeah, so abelian group with respect to the operation of the group is what where
Suppose operation is plus. So what are the properties for
it is
group to be
commutative
abelian?
with respect to that operation. Yeah, so for all A, B in R, A plus B will be B plus A.
Yeah. A plus B
Yeah.
should be there. And what other properties?
Yeah, it
Closure property,
Yeah,
has to
this
follow
is
other
first one is
properties
a
of the
closure
group.
property,
closure
right?
property.
Like it
Second, an
will be
associative property.
yeah, closure.
Yeah. Second one is associative. What is that?
Third one is identity element.
Okay. And the next one?
Fourth one is the inverse properties.
And what? For
Last
abelian?
one is commutative property.
Right. So that is the property we require for this R plus should be abelian group. So there should be these five properties. And what is the property for a group, for a semi group? Anyone can talk. What is the
All other
property
properties
and
except I guess
associative.
inverses.
Yeah, the first two properties, right? Closure should be there and it should be associated. So after this, we have two further properties for it to be form a ring, the natural properties kind of thing. So what is that? So third one is R dot S plus P should be R dot S plus R dot P. And the fourth one is,
Yeah, distributive properties.
yeah. So R plus S dot P is equals to R dot P plus S dot. So this is a definition of a ring. But we want something more. We want with a nice condition. So basically, usually in usual case, what we did, in usual case, we add something more assumption. Or we add commutativity and identity also. So we also want like the fifth condition is that we also want identity with respect to the second operation, multiplication. So we also want that there should exist E belongs to R such that there exists E belongs to R such that A dot E is A for all A belongs to. And we also want that A dot B is same as B dot A for all A comma B. So, right? So whenever I will talk about a ring, usually I will assume all these 6 conditions, right? So basically, the for definition of a ring, we need only 4 conditions. It should be a abelian group with respect to first operation. It should be semi-group with respect to second operation, and the compatibility hold, like the distributive properties should hold. But we usually work with a commutative ring with unity, right? So it should have a unity and it should be commutative. Right? Okay. So let's start.
Excuse me, when you insist on commutativity, why these two distributive laws?
Yeah, what is the question?
Look at the sixth condition, A dot B equal to B dot E, right?
Yeah.
Then why you have 3 and 4?
Yeah, then it is same. But if you are working with non-commutative setup, then they are not same, right?
Yeah, because the semi-group need not be abelian type of in general. Like this.
If you are assuming this 6th condition, then you can remove one of the 3rd or 4th, then both will be equivalent. If you are assuming that A dot B should be is same as B dot or B dot A for all A comma B in R, then the 3rd and 4th are equivalent. Right? You can prove that. One whole then.
Yes.
Yeah.
They are like left and right distributive ones.
Yeah.
But
Okay. So give some example of rings, right? From where I will add next to, let me see. Okay, here I can add. Okay, so give some example of ring. Okay, anybody can give some example of ring? Okay, let me start. Is this a ring?
Not your ring.
Is this a group? With respect to plus operation, right? Is this a group? Natural number comma plus is a group?
No.
no.
Why?
Inverse property is not satisfies.
Inverses doesn't exist for yeah.
Okay, and what other? Is there identity?
No.
No. Identity is also not there.
For plus operation, 0 will be identity and it is not in the set of natural number, right? Okay. So the next natural is integer.
Z plus dot is a group, a ring.
Yeah. Yeah. Tell me. Yeah, this is a ring. So what will be like Z plus is a group you know. I hope that you all know Z plus is a group. So we only need to check other conditions. And I hope that hello.
Yeah, the other conditions are satisfied because in semi-group we are not asking for something like inverse and so that is easily satisfied.
Your audio is not clear for me. Can you say again?
Like it's closed under multiplication.
Okay. So basically it's simple. You can check that it's a ring. I hope that it is done in class.
Yeah.
So okay. Okay. Let me give you something interesting. Okay. Let's increase this thing. R plus is abelian. R dot is semi-group. These two compatibility condition holds and identity there. Now, if the 6th condition is not there, right? If the 6th condition is not there, A dot B equals B dot A is not there, and I also give you inverse for every non-zero element. Then it gives me something more, and we call them division rings. Okay. And if you add the sixth condition also, then and the inverse also, then this is a field. And we have a famous examples for this thing like Q and reals, complex, all these are done in your class. Like I see notes and it is done in class. So these are fields. So let's do something and let's start with some examples. Basically, let's not do first example. Let's do some properties first and then do example. Okay. Let me check. Okay. Wait a second.
You are not audible.
No, sir.
Hello. Hello.
Yes, sir.
Am I audible?
Yes, sir.
Yes.
Okay. Okay. Let's start. So see some properties. Let's start. Then we will do some examples and something more. So it's just obvious. I am just doing that how much you are understanding. So let's do this one first. Okay. Can someone give some idea how I should prove this one? For A belongs to R. For all A belongs to. Where R is R plus dot is any ring. I am assuming. So how to prove this? Give me idea. Writing a proof will give you more idea, and then you can naturally solve exercise problems if you write the proofs on your own. So let's think something. How we will do such kind of proofs?
Start with 0 plus 0 dot A.
Yeah. Okay, let me write 0 plus 0 dot A. And now it is same as 0 dot A. Now this thing is same as 0 dot A plus 0 dot A, right? Right. So now what?
Equate and use cancellation law with respect to addition.
Yes, sir.
Yeah.
Yes, sir.
So then you get 0 by using cancellation law, you get 0 dot A is 0.
Yeah. Zero
Similarly, by just
is the only number which satisfies the thing that n plus n is n. Yeah.
yeah, similar way you can get A dot 0 0 if you are working with non-commutative setup. If you are in commutative setup, then you are done for this.
Yeah.
So okay, let's do second one. This is just simple thing, but let's do once this one. A dot B, this is nothing. A dot B is minus of A dot B. Okay, is same as A dot minus B. How to do this?
Add A dot B to all of these. Try something else.
Can you tell again?
Yeah. Add A dot B to all of these. One will give 0 and other something.
Where I have to add A dot B?
Maybe, add it from the left.
Okay. Okay. A dot B plus minus of
This
A dot B. So it is 0, right?
and we have distributive properties also to support.
So where I have to distribute?
Start
will
with
have-
A.
Yeah.
Start
so
with A
in the
plus
second one
minus
we
A
will have-
dot B.
Yeah, that is the correct idea. So this is not correct, right? From here we cannot proceed.
In the second one, we will have A dot B plus minus A dot B. B will be common, and then you can use distributive property to say that A plus minus A dot B will be 0.
Yeah. So
Yeah, so that will be only.
okay, you can think about your argument, can send later if you have some doubt, or can you ask next?
Yeah,
time?
fine.
So let's do in this way. A plus minus A is 0, right? And 0 is equals to 0 dot B. So 0 is equals to, I can replace 0 by this one. A plus of minus A dot. But this is same as 0 is equals to A dot B plus minus A dot. Now you can just do this one. This one implies you can just take A dot B this side, and then this is same as A dot B, same minus of A dot B, right? In doubt?
One is the inverse of the other.
Yeah.
One is the inverse. Sum of two things is 0 means one is the inverse of the other. Minus A dot B is the inverse of A dot B.
Yeah.
Inverse of A dot B is denoted by minus of A dot B.
Yeah.
So that
This
way
is additive inverse, huh? Not multiplicative. This is additive inverse. Right?
Yes.
Yeah.
Additive inverse. Additive inverse of A dot B is minus A dot B.
Yeah.
Additive inverse of A dot B is denoted by minus of A dot B.
Yeah. It
Why
is.
taking right side element to the left side and all those things?
Okay. Additive, yeah, additive, yeah, you can do that. Okay. So let's do some example. Do you guys familiar with units and nilpotence and these things in a ring? Or should I give definition? Someone can respond.
Can you please explain how to find units of a polynomial rings?
Okay, fine. Okay. Okay. Let's start. What is a polynomial ring? Okay. Suppose R is integral domain. Okay. So I am assuming integral domain. What is the integral domain? Are you familiar with definition of integral domain?
So it has no zero divisor.
Yeah, commutative ring with unity which has no zero divisors. Okay. So means zero divisor means for a non-zero element you are not getting a non-zero element which annihilates it, right? So making zero. Okay. So R is an integral domain. Then we are saying Rx is a polynomial ring in one variable. So what is this? So this is of the form A naught plus E1 x plus E2 x plus so on so on. En x to the power n, where x is some variable. Matlab, so yeah, you can say this is fx, such that this ai, this coefficients belongs to okay. Okay. So now you ask that what are about the units of this ring, right?
Yes.
So what is a unit? What is the definition of a unit? So an element A in a ring R is said to be unit if you get something B and like, okay, let me write, A belongs to R is unit if there exists B belongs to R such that A dot B is one of R, matlab unit of R. Okay, so here elements A and B in polynomial ring are simply polynomials. So let's assume we have two polynomials, fx and gx belongs to Rx. Fx is equals to A naught plus A1x plus so on so on so on A n x to the power n, and gx is equals to B naught plus B1x plus so on so on so on Bm x to the power n. So now, okay. So now, do you know multiplication in polynomial ring?
Yes.
Okay. So tell me how to multiply these two polynomials.
Yeah, so like x powers of x will multiply like they are usual and their coefficients will also. So it will be
So tell me what is
A0
the
B.
multiplication of these two polynomials?
Yeah, so A0 like yeah, so each element of fx will multiply with each term of gx.
Okay. So let me write A naught B naught plus A naught B1 plus A1 B naught x plus what is here? Let me write here also one element more.
A0 B2.
Yeah, you can write this one here also. B2 x square B2 x square.
X.
Yeah. So now
So yeah,
A naught
A0 B2
B2, then A1
plus A1 B1
plus
plus A2 B0
A2 B0, right? X square plus so on so
X
on.
square
Yeah, you can calculate
and
it.
so on up
Yeah.
to x raised to n plus 1.
Yeah. So if some polynomial fx belongs to R, then we have some polynomial gx such that fx dot gx is unit in Rx, right? So that is 1, right? It should be same as 1. Agreed or not? If some doubt, you can ask. So this can be, I can write this as 1 plus 0 dot x plus 0 dot x square. Yeah, this way. Is it clear or not? Please respond. Otherwise, I will not understand you. Are you getting or not?
Yes, it's clear.
Okay. So now what I will do? Okay. Tell me what I should do. Okay. Similarly, I can compute gx dot fx, right? I am not doing, but you can do if you are working with non-commutative setup. Otherwise, these both things are same. But if you are working with means okay, I will assume always I will working with commutative setup. Otherwise, I don't want to do this non-commutative stuff. So let's assume I'm always working with commutative setup. So I will not do this side. Okay. So now what I should do?
Yeah, equate powers of x with the powers of x of
Yeah,
the like left hand side and right hand side with same power of x only.
yeah, correct. Okay, so why it is not working? Okay, okay. So equate just both sides. So a naught b naught should be 1 and a naught b1 plus a1 b naught should be 0 in similar. Okay, so from here what you get? What you get? This a naught is unit in R, since you get some b naught in R such that a naught b naught is 1. So a naught is unit in R. Okay. Okay. So what you get last term? So just tell me this last term. What you get here? Anyone can respond? You will get here an bm x to the power m plus n, right? M plus n.
Yes.
Yeah. So by equating, you will get an bm is 0, right? Right?
Yes. Yes.
Yeah. Since an is non-zero and bm is non-zero, because I will assuming that okay. So let's assume that this highest degree coefficient is non-zero. Otherwise, you can just work with, suppose an 0, then you can work with an minus 1. So you can assume highest degree coefficient is non-zero. Okay. So an bm is equals to 0, but an non-zero and bm non-zero. But this is a contradiction since you are in an integral domain. So that means, so this is a contradiction, right? Right. So this implies n should be must be 0 if it is a unit in a polynomial. If it is a unit in a polynomial ring, then n must be 0, and you are getting, so n is 0, that means the polynomial is just of the form fx is equals to not, right? Where a naught is a unit in R. Now, what about the converse implications? Means I want to claim that this is a polynomial f of the form a naught plus a1x plus an x to the power n of degree n is a unit in polynomial ring Rx if and only if a naught is a unit in R. So I prove that if fx is a unit, then a naught is a unit in R. So what about converse implication? Your question, I guess, only this side, but we can do converse side also. This is if and only this. So let me write something. Okay, we will do converse also. Let me write first statement here. Let's write.
Excuse me, you are defined polynomial rings only for R is an integral domain.
Yeah, I write about.
For any general ring, you cannot define polynomial ring.
We can define, but I just don't want to work with this nilpotents. Yeah, you can. They're the only unit of the form a naught is unit, and the rest terms are nil. You can figure out this. You can define polynomial ring over any ring, even need not be commutative, but yeah, the things will be not nicer there. Okay, so let me write this proposition. a polynomial f(x) is equals to e naught plus a1x plus n x to the power n of degree n is unit in polynomial ring Rx if and only if not is unit. Okay. Okay, so let's see one side implication we already done.
Also, A naught is unit and rest of the terms are zero.
Yeah,
A naught is unit and rest AI are zero. Don't we need it?
okay, you are claiming the polynomial if a naught is a unit, then are you claiming the polynomial gx?
Like other terms have to be zero, no? I guess
Okay,
if it has to be zero.
okay, let's see. So what you are saying, the candidate for gx? Okay, there is this one. We are proving the converse implication, right? So okay, what is your candidate for gx?
Inverse of A naught.
Inverse of a naught. Let's b naught is inverse. Okay, you are saying this is the candidate for g and rest term are 0, right? Yeah, 0 dot x plus so on so on. So. Okay, so what is fx dot gx?
You won't get one.
This is a naught b naught plus a1 e naught x plus everywhere you are multiplying by just a b naught. Okay, so a naught b naught is 1. This is 1, right? Okay. Okay, I guess here we need also the condition n is equals to 0. Otherwise, this is not true, right? That's why I'm saying filling this one. N is equals to 0 means this terms a1, a2, an should be 0. These all terms should be 0. Then you will get these terms out.
Yeah,
Then
yeah,
you are
that is what I was asking.
yeah, then yeah, you are correct. So then this is 1. So then you are there. So this is the proposition. So means I think I remember this incorrectly. So I guess this is correct now. So a polynomial fx is equals to a naught plus a1x plus so on a n x to the power n of degree n is unit in polynomial in Rx if and only if a naught is unit in R and n is 0. Means the, yeah, this a1, a2, an are 0. Okay. Okay, so this is the one question. Okay. So other questions? Okay, let me ask you one question if you don't have any question. So question. Give an example of ring. Okay, we are doing unit question. So let's do first unit question. So I just want to ask, okay, where my eraser? This is so where is this is yeah. So question. So you have to prove sum of unit plus nilpotent is unit. is equals to n. Okay. This is the question. If you are taking, suppose 1 is always unit in every ring, and you have an element X in the ring R, which is nilpotent. Nilpotent, you know definition of nilpotent? Anyone can respond?
Yeah, so there exists and yeah,
Yeah, there exists n such that x to the power n.
you
is
say,
three.
you say.
Yeah. So this is the definition of nilpotent. So if a ring, suppose you are working with a ring R, commutative ring which unit you always assume. Okay. So unit, one is unit there and an element X is nilpotent there. Then I am saying if the 1 plus X is unit in R. So how we will prove such kind of things? Okay. Anyone have any idea?
So if X is a unit, nilpotent element, and then so will be minus X. Like minus X is for 2n will be X is for 2n.
Yeah, yeah. Then fine. Then what?
So 1 minus X will always.
For a unit, why you are taking 1?
You can take anything else, but first I am doing basic case. Like then I will conclude for something more. But I am just doing basic case. Okay, let me argue first. Then we will do proof. Suppose you have any unit U, and then you want to prove U plus X is unit in R, right? But you are already done if you prove this one, right? How? I will say. Suppose then if U is unit, then you have something V in R, so that U dot V is 1, right? Then U dot V 1, so you can multiply this by U plus X dot V. This is same as UV plus XV. So this is 1 plus XV. Now you can argue if X is nilpotent, then XD is nilpotent, and you will done by this case first. So that is my idea to do this. So first prove that this 1 plus X is unit in R. Okay. So any idea?
X power n minus 1, where n is the nilpotency of X.
Okay. So let me write. Where is this? X to the power n minus 1. What is this? Why this one happening?
X power is n minus 1.
Okay, power is n minus 1. Okay.
UV means
Why this happening? I don't know. Okay. Why this happening? Why?
X is nilpotent means X power n equal to 0, some positive integer n.
Yeah.
You will have to make use of that. Is it not so?
Yeah, I know. But I'm struggling with my pencil. Just 1 second, right? So I don't know what happening here. Why this happening? I'm not doing anything. Yeah. Okay, now it will work. Okay, fine. Okay, fine. So what you are saying? Suppose n is nilpotency index. That means x to the power n is 0. So now what you say? Someone is saying something. What you are saying something like x to the power n minus 1, right? You can say again. Okay, no one has responding, so let me tell. So 1 plus x into 1 minus x plus x square minus x cube plus so on plus minus 1 to the power n x to the power n equals to 1 plus minus 1 to the power n x to the power n plus n plus 1. Okay, so let me write below this one, x to the power n plus 1. So this is the equation. You can check this easily. This is the equality. So in any ring, commutative ring with unity. So this one I am using. So from here you can see, right, you are getting the inverse for this polynomial 1 plus x. Since you can, this one is a nilpotency. This one, right, second element on the right side is nilpotent. So this one is 0. So you are getting 1. So 1 plus x is unit. So this implies 1 plus x. What happened? Oh, where is this one? Right? This one freezes. 1 plus x is unit. So now 1 plus x is unit, then by this argument you are done. But I just not want to do this by. So can someone give me some other idea? I know, means if you are not familiar with these stuff, then I will not say this thing. But if you are familiar with prime ideas and maximal ideal kind of thing, then I can do this by somewhat more easier. So tell me, are you familiar with prime ideal, maximal ideal stuff? Anyone can respond.
Yeah, familiar with those, but
Yes, sir.
Okay. So, what is the definition of prime ideal? Should I give you definition, or do you know the definition? Okay, let me give a definition of prime ideal.
Proper. Is proper ideal and A dot B is belongs to then A, either A belongs to the and B belongs to
B
the.
belongs to the other. So by some effort, you can prove a proposition that I hope you will done this in class. So if not up to now, then you will do this in future. But this is just simple one. So you will prove this in class. So every commutative ring with unity has a maximal ideal. Okay.
yeah, done using Stone's lemma.
Yeah.
Is it done using Stone's lemma?
Yeah. For its proof, you will need John's lemma, right?
Yeah.
Okay. Every commutative ring with unity has a maximal ideal. So what is my idea is that suppose 1 plus x is not unit. Is not unit. Then you can argue that there will be some maximal ideal or prime ideal, something which contains this 1 plus x. There exists a prime ideal. Because in a commutative ring with unity, you can prove that every prime ideal is a every maximal ideal is a prime ideal. Right? So 1 plus x is a not unit. So there exists a prime ideal. P such that 1 plus x in P. So now what is my argument? Can someone guess something or some idea? My x is nilpotent element, and nilpotent element is, so see, okay, let me tell you. So x is nilpotent, that means x to the power n is 0. So 0 belongs to P. Now by definition of prime ideal, x dot x to the power n minus 1 should be in P. So that means either x in P or xn minus 1 P. So if x in P, then you are already done. If x is not in P, then you can do same thing in xn minus 1. And at the end, you can conclude that x is in P. So for every prime ideal, this nilpotent element is in the prime ideal. Okay. So nilpotent element is in every prime ideal. So I conclude that 1 plus x is in P and x is also in this P. So now what I can do? Any idea? Tell me something. Now this is easy. You should respond. Tell me. Prime, any ideal should be additive subgroup, right? So what I can conclude from here? Something contradiction or something. Okay. No one is responding, so let me write. So 1 plus x is there and x is there. So 1 plus x minus x is there. This is means 1 in P. Okay, there means P. This means 1 is in P. 1 belongs to P. But which is a contradiction, right? Contradiction. Right. So 1 plus x does not belong to any. So it is a unit. So in this way you can get. This is also another. So I gave you 2 proofs for the system. Okay. So, okay. I have to insert another page. So add page. Okay. This one. Okay. So any doubt in this proof?
Yes, I have a doubt from here.
Yeah. Tell me. Hello. You are not audible. Hello. Someone is saying something, but I cannot hear you. So, Muthu Kumar's iPad. So
The proof is not clear.
the proof is not clear. So what part is not clear?
So every commutative ring with unity as a maximal ideal is the proposition.
Yeah.
You start with 1 plus x is not a unit.
Yeah. So I am saying that if it is not a unit, it will be contained in some prime ideal. And you can prove this. Every non-unit is inside some prime ideal for a commutative ring.
Some prime ideal.
Yeah.
Then how that x also in P?
Since x is nilpotent element, then I give its proof, right? So let me scroll down below. So from why this one is not working? I'm struggling this with this device. Okay. So here I write this thing, right?
Okay.
This one. Since x to the power n is 0 and 0 is inside every prime ideal. So that means
Okay.
x dot x
Okay,
to the power.
okay. Now when you write 1 plus x, you have to mention that x is nilpotent.
Yeah, x is nilpotent. Yeah, we know this, right?
X is nilpotent. When x is nilpotent, we know 1 plus x is a unit.
Yeah, that one, that's we have to prove, right?
Every ring has a maximal ideal is what we have to prove.
Yeah.
What is that assumption which contradicts finally?
This one is in the prime ideal, right? I got this thing, but one cannot be in prime ideal since it is a proper ideal.
So your conclusion is therefore 1 plus
ideal.
therefore 1 plus x is a unit.
Yeah.
Then how you are proving that every commutative ring with unity has a maximal ideal?
I'm not proving this. I just say this is the statement. I just using this.
So you are trying to prove only 1 plus x is a unit.
Yeah.
Then
I
why
gave some other proof for this. I already proved this by one another way,
Okay,
but I'm
okay.
just giving this.
So for that you are using the proposition that every commutative
Yeah, means when you are
has a
when you will
maximal
prove
ideal.
this 1 plus x is contained in some prime ideal, you will use somewhat this idea. Every commutative ring with unity has a maximal ideal. Means if 1 plus x is your non-unit, then you are.
Then x into x power n minus 1 belongs to P means how you say that x belongs to P?
Okay, x dot x to the power n minus 1 is P means either
Yes.
x in P or this one is in P. So if x is
Yes.
in P, then we are done. But if x to the power n minus 1 is in P, then you can further write this as x dot x to the power n minus 2. By similar way, you can continue in this similar fashion, and then you can conclude.
So that explanation you have not given. Now only
Yeah,
you are
but-
I given this explanation, right? I talked, but I didn't write.
okay.
No, that's by induction. Yeah.
Yeah. So let's go ahead. Do a further questions. Some further questions. Okay. Okay.
Hello?
Here is this one. Okay, here. Question. So anyone have any doubt?
Yeah, hello? Hello, sir? Yeah. Sorry, maybe for the last line here. We have used the fact that 1 plus x minus x. So we are using the minus because we know it is a group, right?
Yeah.
Okay. Thank you.
So, okay. Okay. So give me some examples of a ring. Okay, let me ask. Give an example of a ring such that AB equals to AC, but B does not equals to C. Means the cancellation law does not. Can someone give some example of a ring? Or is it true statement? If not, then give me counter example. If true, then give me proof. Anyone interested?
Yeah, so A can be 0 as well. So yeah, A can be 0 as well, and still first condition will be followed.
So if A is 0, then how you will conclude? Okay, okay. And then you can change B and C different. Suppose A is non-zero. Then what? Then can you say this thing? Let me write. A is non-zero.
Yeah, in some matrix example, yeah, the matrix example can follow.
Okay, I don't want to go non-commutative setup. So what about commutative setup?
Then it
You
won't
can try with
concentrate.
ring of integer modulo n.
Yeah,
For a
you can
suitable
work.
n.
Think about this ring, right? Z by nz. Think about this ring, but don't think about
Yeah.
when n is prime because it is a field. I guess Harish did this. He told me that he did this example in his tutorial. So I hope you all are there. So if n is prime, z mod pz is a field. So then it will hold if A is non-zero because it has a inverse. Then you can conclude that B is C. But work something else. So can you say something when n is not prime? Think about this.
You take a n which is not a prime number.
Yeah. So give me something. So let's work with Z mod 6Z. So what will be the candidate for A, B, C? Can someone give? What will be A? What will be B? What will be C? Such that AB equals to AC, but B does not equal to C.
Yeah, so A can be 2, B can be 1, and C can be 4.
Okay, tell me slowly. A equals to 2, B equals to
V1
B1. And what C?
and C4.
C?
4.
So AB equals to 2, but BC equals to 4. And 2 does not equals to 4 in Z mod 6Z, right? So this is not correct. So this one is not correct. So give something else.
Oh no, I'm saying AB and AC we have to see now. You are taking AB and
Volvo.
BC.
A is 2, B is 2.
Oh, okay, okay.
C
Sorry.
is 4.
Okay, I think.
Sir,
okay,
if we
sorry,
take-
sorry. 2, 1, 4. So AB is 2 and
To
AC
B
is
equals to 3.
8, but 8 is same as 2. Like Z mod 6 Z mod 8 is same as 2. So then this is, but B is not same. Yeah, you are correct. Okay, sorry, I am thinking like AB and BC, but I am saying AB and AC. Sorry. So what else?
Sir, I want to say one thing.
Yeah. Tell me.
A equal to 2
Okay.
in a Z6, A equal to 2, B equal to 3, or C equal to 4.
A equals to C equals to 4. Okay, what is AB? AB is 6, that is 0, and BC is 6 and 12, that is also 0.
And 4 into 3 is 0.
Yeah, B and does not equal to 3. That is also correct. Okay. so
AB
anyone-
must be equal. Sorry, AB must be equal to AC, not BC.
Oh yeah. I am again confusing with 3.26 and AC 4.28. Okay, so it is not correct. Sorry. AC is 8, but it is 2, so it is not correct. Yeah, sorry for that.
Yeah, it is equal to Taifa. I love you.
A not equal to C. So my top one is
So yeah, you can give something other also. Like there will be something more. Not only this one, you can find something else. So anyone also want to participate in this question to give something, or should I go ahead? Okay. Question. No one is participating, so I will write question and you will answer.
Yeah, you can take 3 to 4. That will be fine.
Yeah, okay, fine. Okay. So give an example. Okay, let me ask. If R is a commutative ring with unity, I will always assume this assumption, and A, B in R, then is this correct or not? A plus B is unit in R. A dot B is unit in R. Which of them is correct? Which of them is incorrect? Either both are correct or both are incorrect. So tell me.
Given if A and B are unit,
A, B belongs to R, and A and B are unit. Okay, I should write these things. A
okay.
and B are
1 and minus 1 are units in Z, but
Yeah.
1 plus minus
One-
1 is not a unit.
yeah, correct. So first one is obviously incorrect. So this one is incorrect. So what about second one? So if correct,
B-
then give me
Second
proof
one
if
is-
it's correct. So give me counter example. Yeah,
Second one is correct.
this is correct. You are saying correct?
So, like if C, yeah, second one is correct. For A, C, yeah, C is the number such that A.
Okay, what
C
is your
equals to
candidate
C,
for
A equals
inverse?
to 1, and then if
B
C is the
inverse, A
number,
inverse.
so
Okay.
yeah,
Okay, right.
B inverse.
A dot B
that can make it. Course.
dot B inverse dot A. Okay. So this is A dot B inverse dot A inverse barabar. So this one is identity, and then you can say A dot A inverse is identity. So that this is identity. So this one is this is correct. Okay. So let me take some question from this one book. Some simple question from this book. Okay, I am giving. Okay. So are you guys familiar with definition of a Boolean ring? I hope not. So
Yes.
Yes, sir. Yes, sir.
definition familiar?
Yes, sir. For all A belongs to R, A square equal to A.
A square?
Equal to A.
Okay, correct. So this is the definition of a Boolean ring. So I am giving you a question. Okay. Okay. 2x is equals to 0 for all x in R, where R is a Boolean ring. R is a Boolean ring. So Boolean ring means x square equals to x for all x in R. So anyone have any idea how to prove this thing?
Yeah, so take x plus x whole square equals to x plus
Okay, so someone is
x
giving
and
some
then
idea. Wait a
open
second.
the square.
Yeah. You are saying write x plus x ka,
Whole square
and it should be same as,
equals to x plus x.
right? By
Because
definition of a Boolean
x
ring.
plus x.
So this
Yeah.
should be, this will be x plus x dot x plus x,
Yeah.
x plus x same as x plus x, but you can see
Yeah,
what is this x
x square 4 times.
square,
Yeah.
x square plus x square plus x square equals to x plus x. But see, x square equals to x, so all are x plus
And then same x plus x plus x plus x.
equals to x plus x. Then you can, then you are done there, right?
And then club 2x with each.
Yeah. Then you are done, right? 4x is equals
Yeah,
to
you're done.
So I have to add a place. Okay, here is some space. So second one is, you are familiar with definition of unit and nilpotent both. So I will do second part. So let's see if someone participates with me or not. Every element of R is either unit or nilpotent. R is either unit or nilpotent. This one we have to prove. This is interesting. So anyone will give some idea to me? Some idea? Anyone can respond. Okay.
R is given Boolean ring.
Yeah, this is Boolean ring. This question is for Boolean rings. This is first part. This is second part. So R is Boolean. This one is Boolean. Okay. So how we will proceed? Suppose X is not unit, then we have to prove it is nilpotent. Suppose X is not unit, then what we? Respond, please.
Yeah, so there doesn't exist any element in R such that XR will be 1.
Your audio is not clear.
Yeah, so if X is not a unit, then there doesn't exist any small r in R such that XR equals to 1.
Okay, then what?
Then
Then what?
take its square, XR square will be X square. Y square.
Okay, let's start. So do something else. Okay, so X belongs to R. Okay, suppose X belongs to R is non-unit. This, what this means? there does not exist y belong to R such that xy is 1, right? So now we have to conclude in some way this x is nilpotent. So what x is in R, so x square is same as x, right? Wait a second, I have gotten something. Yeah, tell me. Okay, so x square equals to x. This means x or x minus 1 is equals to 0. Okay, so we have to conclude either unit or nilpotent. So how we can conclude this? Okay, this one is in P. Okay, this one is in prime ideal P for every P. 0 is in every prime ideal, right? So by definition, okay. Okay, so what we can conclude from here, let's see. We have to show this belongs to every prime ideal X. So
is a Boolean given to be commutative or something?
yeah, it is commutative. I am always assuming.
So you can multiply x minus 1
by what?
With y and then show. You
What you are
can
saying?
multiply x minus 1 equals to 0 by y, both sides.
Okay, let's multiply by y. Xy is equals to x minus 1
equals to 0 by equals to 0.
Then what?
And then xy is 1, so x minus 1 has to be 0.
Why xy is 1? There does not exist any y, right?
Because we have taken that xy equals to
1. Where if we take this xy1, I said that there does not
just that xy equals to 1.
Okay, I am saying there does not exist any y such that xy equals to 1. ऐसा कोई y exist ही नहीं कर रहा है.
Okay, yeah, okay.
So how we will proceed from here? So this x and x minus 1 is in every prime ideal. So from what we can conclude? Think in this way, like nil radical is intersection of all prime ideal. So try to show that x is in every prime ideal. Here I am using a definition, you can say this. Nil radical.
Oh yeah, so then x is in P or x minus 1 is in P.
Is equals to intersection of prime ideals.
Yeah.
So, okay, so someone is saying something, tell me.
No, that's not what I was saying.
That means either x in P or x minus 1 in P. C. But x minus 1 cannot be, okay, how we can say x minus 1 is not in P? We have to say this one.
Yeah, that we got.
We have to say this one. X minus 1 is not in P. So if x minus 1 is in P, so x minus 1 ka whole square is x minus 1, right? So this means x square plus 1 minus 2x, right?
Yeah.
Is equals to x minus 1, right? But this is 0, right?
Yeah, this is 0. Why this is x minus 1, not x plus 1? Oh, okay. Yeah, fine.
So from here, what we can say? X square plus 1 is equals to
1 is x minus 1.
So from here, what you can say?
Yeah, x plus 1 is x minus 1.
X plus 1 x minus 1 x square plus 1. Okay, x square. That will
no, I'm saying just replace x square with x because it's
X square minus 1 should be
Only
same.
that.
Yeah, x square plus 1. Okay. So, okay. Something there. There is something.
Oh, it's fine. The x square plus 1 will be x plus 1.
Yeah, right. That is correct. But,
Yeah, that.
but we have to do something, right? To show this one. This is same as x square minus 1. Can you see? Not x square minus 1, but
Yeah, it's fine. You can take that. X plus 1. You can take it.
yeah, we cannot take that. Okay. Okay, so x square. Yeah. So x plus 1 ka whole square is same as x minus 1 ka whole square, right? This is the thing. Are you agree? What from here? We have to show some way that x minus 1 is not in P, cannot be in P. If this is in P, then x minus 1 ka whole square is x minus 1. This means x square plus 1 is same as x minus 1. Okay. So what we can say from here? Okay. So if x belongs to R is a non-unit, then x is in some prime ideal P. Okay. Now we are done. Right. Sorry, this argument is missing here. Okay. Let's erase this. This. This is the assumption we are missing. Okay. Since x belongs to R is a non-unit, right? X belongs to R non-unit. That means there exists prime ideal P such that x belongs to P, right? So for this P, right, you will get some contradiction. This is the same P. So x belongs to P, right? So if x belongs to P, then x minus 1 cannot be in P. X minus 1 does not belong to that P, right? Because if x is in P, then x minus 1 cannot be in that P, since x minus 1 minus x minus x minus 1 is 1 in P. That will imply this one, but this is a contradiction, right? So this means
Yeah.
So this means this x minus 1 cannot be in that P. So x should be in every P, right? But how x in that P? So we conclude that x minus 1 is not in that P. So okay. Something missing. But there will be some argument like this. So I will continue this in next lecture. Maybe I am missing something. So next lecture. Yes. If anyone have some idea, I can do, but I am not getting this thing right now. I just take this exercise. I don't know how I can test it. So there are some participants who are interested. So anyone can give some idea. Okay, fine. Let's go ahead. I will do this thing next time. Next lecture. So do something else. This is the beauty of mathematics. How many times you done is exercise, but this cannot be done at some time. So तुम कितनी ही बार कर लो, एक बार नहीं भी हो सकती है. So this is the thing. So you should. Next time I will do this one. Okay. So we should do something else. Okay.
I have a question. So if we define the ring as A plus B, where A and B belongs to real, would the multiplicative inverse be 1 by A plus 1 by B or 1 by A plus B?
Okay. Tell your question again right now. I have to write.
If R is the ring defined such as A plus B, where A, B belongs to real numbers.
Question. Okay. Tell me, what is the question?
R is the ring which is defined as A plus B, where A and B belongs to reals.
Ring R is defined as A plus B such that A comma B. Right? So what is your question?
Yeah. Would the multiplicative inverse be 1 divided by A plus B or 1 by A plus 1 by B?
For what element?
Because for the same thing, for A plus B. So because they say only AB belongs to R, so my question is, would 1 by A plus 1 by B be the multiplicative inverse, or 1 whole divided by A plus B be the multiplicative?
So have you done calculation for this? How you try to compute this? What is your approach? Suppose A plus B you are taking. What is your candidate for inverse you are saying?
I think to get the identity for multiplication, the identity is 1. To get it, I think it should be 1 over A plus B. But if it's real, it works because we know 1 over A plus B belongs to R. But since they have defined it, they did not say A plus B belongs to R. They just say AB belongs to R.
Let's stop. So do you know inverse is unique?
Yeah.
Do you know inverse is unique?
Yes.
So if 1 upon A plus B is inverse for this, then why you are saying that means is this a inverse or other is a inverse? If this is a inverse, then only this is a inverse.
Yeah.
Right?
Okay, that works with reals. So if they define some other domain, if A plus B does not belong to that domain, then we can't say 1 over A
plus B should be in that domain by the definition.
No, if at all we consider a different domain, like if it's not real.
Okay, so what is your question? Okay, this ring R should be not real, so this should be anything, something other ring.
Yeah.
Or you want to say this?
No, I don't have. But what if there is case where A plus B does not belong to that domain?
Why if A plus B is not in that domain? Okay, now.
Okay, I got it. I got it.
Okay. Okay. Oh, yeah. So. Okay, let's write a question here for you. This is also a question from Atiya McDonough. In a PID, okay, okay, okay. Are you guys familiar with in a PID every non-zero prime ideal is maximal? I hope I will not need this statement in this book, but let's see. Okay, what is the question? R is a ring. Matlab ring matlab commutative ring with unity. Commutative ring with unity. Such that for every element to the power n equals to x for some n bigger than 1 to show every prime ideal P is maximum. So we have to show every prime ideal maximum. So how we'll do this? Do anyone have any idea? Anyone can give me any idea? Are you familiar with this statement? Okay, we will use here some statement. R commutative, this is a proposition I will use here. R क्या है? Commutative ring with unity, then R is a commutative ring with unity, then P is a prime ideal. If and only if R mod P is the integral domain. Integral domain. This is an easy statement. You can just see by definition. P is a maximal ideal if and only if R mod P is a field. Okay. Okay. So okay, so from this you can conclude that since every field is an integral domain, so every maximal ideal is a prime ideal for a commutative ring with unity. So this two thing, this thing you try to use here. Okay, I have an idea. We can do this question. Okay, let's do first this question. If we will prove this, then that one will be automatically done. Okay, let's prove this one. I have an idea. Okay. So any idea? First, tell me, are you familiar with these two statements? P is a prime ideal, R mod P is an integral domain. Anyone can respond.
Yes, I'm familiar with it.
Okay, fine. Okay, then go ahead. So how to prove? So I have to prove every prime ideal is maximum. So let's take a prime ideal. I have to show it as a maximum. So if I have a prime ideal, then R mod P is the integral domain, right?
Yeah.
So if R mod P is the integral domain, I have to prove that every non-zero element here is a unit, right? Then it will be a field.
Yes, sir.
Yeah, so I have to show, I have given this x to the power n equals to x, and by using that, I have to show that for every non-zero element in R mod P, I have a inverse. That means that R mod P is a field. That means P is a maximum, right?
Yeah.
So that is the idea. So how to go ahead? I gave you idea. So can anyone do this for me? Okay, no one is participating with me. Okay, let P be a prime ideal. We need to show P is maximum, right? P is prime. This implies R mod P integral domain.
Yeah.
So to show R mod P is field. For field, what we have to do? Every non-zero element have inverse. We have to show. Let me add a place. Where I am. Okay, here is a space. Okay, so R mod P is field. So suppose take a non-zero element. 0 does not equals to x bar in R mod P, right? It is non-zero here means it is outside P, right? In this ring, non-zero means it is not in P. So right, you have this thing R to R mod P. Here the element x goes to x bar, right? So x bar not in P. So what we have? So for this x bar, I have an element x in R. Okay, so x in R such that we have given that x to the power n is x. That means x dot x to the power n minus 1 is equals to 0. Now, but R mod P is an integral domain. So let's do this in R, this calculation in R mod P, right? So if R we have this inequality, then obviously in R mod P. So this one. But since R mod P is an integral domain, so this will imply either x is 0, x bar is 0, or this one second one is 0. But x bar is non-zero since we assume this one. So this means x bar to the power n minus 1 equals to 1. So this means x bar dot x bar to the power n minus 2 is equals to 1. This means x bar is unit, right? We proved that any non-zero element has an inverse, right? Right? Agree or not? Someone can respond. Is this clear or not?
Yes, sir.
So we proved that every non-zero element has an inverse. So this means R mod P is a field. R mod P is a field. R mod P is a field. So we prove R mod P is a field. This implies P is maximal. Okay. Okay. Is this clear? For we take any prime ideal and we prove that it is maximal. Okay, let's go to that question where we are struggling that time. So in that case, n is x. So x square equals to x we have given, right? Please participate with me, otherwise how I will continue.
Yes, sir.
Yeah. So x square equals to x is given. So there we have. So what there we have? There we have that x square equals to x. That means every prime ideal is maximal, right? So every prime ideal is maximal. Okay. So from there, what we can conclude? I just want to say that nil radical is a prime ideal. So can we conclude from there? Anyone can give something to me? Okay, nil radical is a prime ideal. I have to conclude. Okay, okay, you can do this thing, right? A mod nil radical. In that case, I have to conclude nil radical is a prime ideal, right? R is a ring. That one, in that case, right? I am continuing that case here. So I have to conclude nil radical is a prime ideal. So I can go R to R mod n, nil radical is ideal. So R mod n. So I have to conclude that this is a I am saying that I want to conclude nil radical is a prime ideal, but I will conclude that this is a field, right? So then I am done. So I even want to say more. This is a field. So R mod n is a field, but from this case, if we can go analog, but here P is a prime. So I just need to show n is a prime. How to show n is a prime? Nil radical is a prime ideal. It seems I'm missing something, but I don't know what that. Boolean ring 2x is equal to 0. So x plus x is equal to x. I don't know. Let's stop this one. Okay, we will do this one in next session. So I'm not getting idea for this one. Okay. So anyone want to ask something?
Excuse me, I suggest that you can solve these problems, practice assignment problems.
But that is deadline is 8th February, so I cannot solve that one, right?
Practice assignment problem, not assignment problem.
So where is that given? I don't know. Let me check.
Practice assignment problems.
So let me go to NPTEL site. I have to check. I don't know where that one is. Introduction to rings and fields. week 1. Okay, practice week 1 assignment. Okay, this one is here. Okay, sorry, I missed it. Let's see this where what is here. Okay, let's do this one. This is things. You can see my screen, right?
Yes, sir.
Yeah. So here you have two assignment question, right? So select all true statements. So first one, let R be the ring Z mod 4Z of integer modulo 4. There are non-zero elements in R whose product is 0. Can you give me these elements? Is it correct or not? Okay, I have to write if you. Okay, if we have given. Okay.
It is correct because
Correct.
2 times 2 is 4, modulo 4 is.
Okay, we have ring R is equals to Z mod 4Z, and we have to say that there are two elements A and B in R such that AB equals to 0, but A and B non-zero. A does not equals to 0 and B does not equals to 0, right? Okay, so AB equals to 0. So what is this element? Take A equals to 2, B equals to 2. That means 2.24 is 0 here, but 2 does not 0 and 4 does not 0. So this one is correct. So what is this statement? R be the ring integer module. There are non-zero elements in R whose product is 0. Okay, this one is correct, right? Okay, so R be the ring Z mod 5Z of integer modulo 5. There are non-zero elements in R whose product is 0. Okay.
No, sir.
Why?
Because Z by 5Z is forms of field, sir.
Okay. So have you done this proof?
Yes, sir. I find all the non-zero 2 element which does not give 0. Either
Okay.
it is 0, then
Then you can directly use this statement that this is a field, so there cannot be a 0 devices, right? So is Z mod 4Z a field?
no, sir.
Why?
Because it has a 0 divisor, sir.
So what?
So it does not have inverse in that ring.
How you will conclude this?
Here, sir, 2.
Suppose it has a, okay, this one is
Yeah.
Z mod 4Z, we have 2 is 0 divisor. So how you will claim that this does not have inverse?
Because 2 does not have inverse in Z, 4Z.
In Z mod 4Z, how you will conclude this does not have inverse? Tell me. You can respond, right? You are correct, but just tell something, how you are thinking this one. I just want to know that.
Because 2 does not have inverse in Z by 4Z, sir.
Yeah. So how you will conclude this? That's what I am saying.
In Z by 4Z, the
Suppose
elements are,
you
sir,
know that 2.24 is 0, and you suppose that it has an inverse. Then what will happen?
Yeah, it should be equal to 1.
Yeah,
the
so
product.
it should be equal to 1. So suppose
Yeah.
there will be an element in A in Z mod 4Z such that 2.2 is A is 1. I should not write this bracket. Why? What I'm doing. So 2.A should be 1 for some A in Z mod 4Z. Then what? Then what? But 2.2 is 0. You can multiply both sides by 2. 2.2.A is equals to 2. But this side is 0, right? 0.A is 0. So 0 equals to 2. This is a contradiction, right? So you can.
Yes.
So from here you get a general idea that any 0 divisor cannot have inverse in any ring. This is just a Z mod 4Z, but you can analog say, you can do similar proof in any ring. For 0 divisor, you does not have inverse, right? So this one is the incorrect statement. This one statement you already told that we have done. Z mod 5Z is a field. And then after that, if R be a ring, the units of group R form a group under multiplication. Okay. So is this correct or not? If correct, tell me proof. If not, give me counter example. Participate with me.
Repeat the question, sir.
This one, R be the ring, the units of R form group under multiplication. Is it correct or not? Okay, let's check. R be a ring and it's take its unit, then we check the axioms of group. If it is satisfied, then it is done, and if not, then it is not. Then it is not a group. Okay. Okay. I have to add a page. Okay. Suppose R is a ring. For me, ring is always commutative ring. Okay, I guess it is given here. It is commutative ring. Okay, I hope that he is working. Okay, then it is. Let's see. R is a ring. So we have to prove that units of R, I am denoting as UR, units of R forms group under multiplication. We have to check this is true or false, right? So what is first one? First one is a closure axiom. So suppose A and B belongs to units of R. Then how we already proved that AB also in units of R, right? In this assignment, yeah, I have done this already. So then associativity will be obviously there. This is just an operation based property. A, B, C in units of R. Then A, B, C, you can say this is same as A, B, C. Yeah, this is just an operation based property. If the ring, then its subring always have this property. So third one, identity. This one will be always there. One is always there, right? One dot for any A belongs to UR, there is a one such that A dot 1 is equals to A and equals to 1 dot. If you are working with one. And the fourth one is if A is a unit, then A inverse is also unit because A dot A inverse equals to 1 equals to A inverse dot A. So it is a group, right? All the four properties satisfied, right? Agreed or not?
Yes, sir.
Yeah.
So it forms a group under multiplication, right? The ring of integer exactly had 2 units. Correct or not?
Yeah. 1 and minus 1.
Okay. So how you will say any other element is not unit?
Because apart from 1 and minus 1, they does not have inverse in Z, sir.
How you will conclude this? That's what I am asking.
Suppose we are taking 2. So we can conclude that 2 into something integer gives 1.
Yeah.
But under multiplication, so suppose 2 into A is equal to 1, so A is equal to 1 by 2. But 1 by 2 does not belongs to integer.
Okay, you can you can sit you can just use that Z sits fully inside Z sits inside Q and Q. If there is an inverse, then and the operations are same, so that the inverse will be same here if that is here. Otherwise, the inverse will be not there. You can use this kind of argument. Yeah, this is correct. The ring Zi has actually 4 units. I guess this is done in your class. I see just your notes yesterday. So this is done in class, right? The ring Zi has units of Zi.
Yeah.
So what are they?
1
minus 1 minus I.
Group under multiplication.
Yeah, 1 minus 1 and for another one?
I and minus
iota and minus iota. Precisely the fourth root of unity. All the fourth root of unity are the units of this. This one is also correct. So only this one statement is not correct. So all these are correct. So what about second one? Is this true or false?
It is true.
It is true. Someone saying it is true.
Set of all units form a group under multiplication.
Right. So
is true.
Yeah, it is true. That's what I did. You want to say it is not correct?
Correct, sir.
It is correct.
So we are doing the second question. Okay. So R be a ring and element X in R is called nilpotent if X to the power n is 0 for some positive integer n. Determine true or false. The ring Z mod 6Z has no non-zero nilpotent element. So you know the elements of Z mod 6Z, right?
Mm.
So you can just calculate, right? Its cardinality is 6. So if any element will be nilpotent, then up to 6 it will be nilpotent. Before, matlab less than or 6 or less than 6 it will be 0. If not, then it is not nilpotent. So we can check, right? But this is all okay. Z mod 6 has no non-zero thing. Okay, if he does not write non-zero, then we can always say 0 is nilpotent. Okay, we have to calculate. So let's do calculation if not clear. But someone should answer this question. You should do this assignment, right? So 1 cannot be nilpotent always, and never can be nilpotent. So let's start. Let's start with 2. So 2 square is equals to 4, does not equals to 0. 2 cube equals to 8, does not equals to 0. 2 to the power 4 is equals to 16, is non-zero. This is modulo 6 is equals to 4. This modulo 6 is equals to 2, right? And 2 to the power 5 equals to 32. So what is this? This is 2 in Z mod 6Z, and 2 to the power 6 is equals to 64. And what this modulo 6? 4. And this is repeated here, like 2 to the power 2 is repeated here, right? 2 to the power 2 repeated here. Okay, so it does not have an nilpotent. 2 is not nilpotent. What about 3? Is 3 nilpotent? 3 square equals to 9 is equals to 3, does not equals to 0. 3 cube equals to 27 is equals to 3, does not equals to 0. Similarly, you can calculate. It is not nilpotent. You can calculate. Just higher powers you can calculate. 3 is not nilpotent. 4. You should participate with me in calculation, right? Otherwise, it is just boring for me doing multiplication again and again.
Excuse me, either you will have to write the problem or you have to show the problem, then only we can able to follow what you are telling.
Okay, so here are the problems.
Where are the problems?
This is the second problem, right?
No, second problem, you have to either show in the screen or you will have to write what is the problem.
You can see my screen, right? Or not?
No, we don't see the screen for the problem.
Oh,
I
you
don't
should
see.
tell me,
Yeah.
right? Okay. So
Yeah,
I thought that you are seeing my screen. Okay, sorry.
Yeah, yeah.
Okay. Okay, let me write the problem there. Oh, sorry. Okay. Okay. R is a ring we have, which is R is equal to Z mod 6Z they are given us. They have given us. We have to check that the statement is that there is no non-zero nilpotent element, right? We have to show this one that has no non-zero nilpotent element. We have to check this is true or false. Statement is this. There does not exist any non-zero nilpotent element in Z mod 6Z, right? This one we have to do. So I already like 0. They are saying non-zero, so 0 is obviously a nilpotent, but they are asking us about non-zero. So 1 cannot be nilpotent since it is a unit. So this is not need to check. 2, I already checked that this is not a nilpotent element. You can check that this is not a nilpotent. 3, I have already done above calculation that it is non-nilpotent. So let's continue with 4. So now participate with me in calculation. So what is 4 square?
16.
16.
No,
But mod 6, it is 4, right?
4, sir.
16 mod 6 is equals to 4. Mod 6, right? And what 4 cube? By similar calculation, you can check that this is also not nilpotent. This is just a calculation based idea. Calculate 4 cube and then do mod 6 and check that it is non-zero. What is 4 cube? Basically, you can check this, right? What is 16 into 4? 64, right?
sir. And
Yeah,
it gives
64
4.
mod 6 is
4.
Yeah. So again 4 and 4 will be good.
Mm.
So it is not important. What about 5? This is last element. Tell me.
256.
But if you know the if you have done this proposition, this is okay, fine. Let's do this. This is okay. 5 square is equals to 25. 25 mod 6. What is this?
1.
1. So that means 5.5 equals to 1. So it is a unit. So it cannot be nilpotent, right?
Yeah.
Not nilpotent. So there does not exist any non-zero nilpotent here. But we see that there are non-zero, there are zero divisors, non-zero zero divisors, but there are no non-zero nilpotent, right? So we see in this case. So what is the statement? Statement says that determine true or false the ring Z mod 6Z has no non-zero nilpotent. So it's true statement, right? So we have done both the question of the assignment. There are only 2 questions in this assignment. So we have remaining 6 or 7 minutes. So what we can do in that? Okay. Let's do something. Okay. Okay. Okay, let's do a last one statement. This seems to be interesting for you. So let's me write and proof it, or you can take it as a question. I am saying this as a proposition, but you can take it as a question, right? This is only a non-commutative setup where this is only example where I am taking non-commutative setup. Otherwise, elsewhere, everywhere I am working with the commutative setup. So if okay, let's assume this one also commutative. If R is a commutative ring with unity, but MNR will be not commutative, right? So let's take R is a commutative ring with unity. Okay, so this one is also non-commutative. If R is a commutative ring with unity, then A belongs to MNR is unit if and only if determinant of A
Non-zero.
Unit in R. So we will prove this one, and with this we will end the class. So let's prove this one. So proof. Let's go forward implication first. Okay. So how we will do forward implication? R is a commutative ring with unity. A belongs to MNR is unit. So A belongs to MNR is unit means there exists B belongs to MNR such that AB
is equal to 1.
equals to identity in N cross N matrix, and BA equals to also identity in N cross N matrix. So what? This is non-commutative setup. So be careful everywhere. We have to do both sides, left and right. So this means that apply determinant both sides. This implies determinant of AB is equals to determinant of identity matrix, which is 1 determinant B. So I guess you know that determinant of AB is same as determinant of A dot determinant of B. So this is 1 is equals to determinant B to determinant A. So this implies determinant A is unit in R. Unit in R. So okay. So other implication. Backward implication. Forward is done. So what about backward implication?
Determinant
We
A is
assume the
unit.
determinant is a unit.
Yeah. So what about, so let's assume determinant A is a unit in R. Right?
Yeah.
So determinant A is unit in R. So what this implies? That means determinant A inverse belongs to R, right?
Yeah.
It is a inverse in R. So determinant A is inverse in R. So what we can say from here? So we know
Determinant.
a linear algebra from basic linear algebra. We know a statement, right? What is that? A dot adjoint of A. You know what is this? You know? Tell me.
Yes,
What
sir.
is this? What is this?
A adjoint
Determinant,
A.
Determinant
determinant of A into
what?
identity.
Adjoint of A dot A. Right? Okay. So what we can do from here? Since determinant of A is inverse, right?
Determinant A is a unit, means it is non-zero. That means A is non-singular. Therefore, A inverse exists. Therefore, A is a unit.
Yeah, you can conclude in. Yeah. So how I will do? A dot I determinant in A inverse. I can operate this one. This is just a entry of R. So adjoint A, this one I'm doing. This thing is same as determinant A inverse adjoint A dot A. This is identity matrix, right? By this one, operating determinant A inverse. So after this, so what we can say from here, we are done almost, right? We have shown that if A is a matrix, then this one is a candidate of inverse, right? So let me see this one, and if yeah, this is a candidate of inverse, right? This one is my matrix B. Yeah, this one is my candidate of B. So if determinant A is a unit, then I produce a matrix B, which is a inverse of this one. And someone is saying some other argument also, that is also nice. But I use this argument because here you are seeing the inverse expression, right? But it is just the same argument, right? Okay. So anyone want to comment something? We are done both sides almost, and the time is almost about to done. So anyone want to say something? There is something in chat box, right? 5 messages. Okay, someone is saying some calculations.
Yeah, sorry, sir.
Yeah, tell me.
Yeah, maybe I would like to comment on the problem that we are doing on the Boolean rings.
Okay.
Yeah, the one that we are trying to show that x minus 1 is not in P.
Yeah.
Yeah, I think there's a fact that we didn't use, that x is not a unit. So if x is not a unit, it means there does not exist an element y such that x minus y is equal to 1.
X minus y. Okay, let me write what you are saying.
Yeah, because there we had x minus 1. So I think this won't be in P, because
yeah, that's what I want
actually
to do, but I got stuck there. So let's write again. So what you are saying?
Yeah, I was saying there's a fact that we assumed that x is not a unit.
X is not a unit.
Yeah, so if x is not a unit, it means there does not exist any y in a ring such that x times y is equal to 1.
Yeah, this is correct.
Yes.
Yeah.
Which actually I think is same as saying x minus 1 is equal to 0, right?
X
X,
minus
x,
one.
x times y, sorry, x times y minus 1 is equal to 0.
Yeah. Yeah.
Yeah. Yeah. But also,
Okay, so in particular, you can take y equals to x, right?
yeah.
X minus 1 is okay. Yeah, that's nice.
Yeah.
Nice. Yes.
Yeah.
Yeah. So we
Yeah.
are done.
Okay.
Thanks,
Yeah.
Thanks for coming.
Yeah. Thank you so much, sir.
Okay. So I hope you all enjoyed this session. So we will meet next Sunday at same time. So this problem already done. So next week I will not do this problem. So as someone give this suggestion and this was done. So thanks for your valuable suggestion. So,
yeah, thank you, sir. Thank you. And also, I think, trying to introduce us on this kind of proofs is very important, especially in this in the ring
means,
theory.
Also, although you are doing rings and force and fields force, but I will suggest you that you can look over the book Introduction to Commutative Algebra by Athiya McDonald first chapter. This is just a rings chapter, and here exercise are really beautiful. Means the exercise I gave you guys. This is from Athiya McDonald.
So can you repeat the name, other name?
Introduction to Commutative Algebra by
Can you message? Can you write the message?
Okay, so let me write. Do its exercises. These are really beautiful.
Yes, sir. Yes, sir, I will do.
Introduction. By Donald Athiya and McDonald. Right. So I have sent you the book name, Introduction to Commutative. Okay, Commutative Algebra by Athiya and McDonald. Right.
Yeah. Oh, thank you, sir.
Yeah. Do its first chapter exercise only. You will not familiar.
So much, sir.
Yeah.
The first chapter.
Yeah, first chapter exercises. There are too much exercises. Do just 1 or 2 exercises each day. They are really hard exercises.
Okay.
Just enjoy this. Okay.
Yeah, and sorry, sir, I have a suggestion.
Yeah, tell me.
I'm kindly asking if I can get the contact, your contact, if maybe I get some problems, I can be able to.
Okay, sure. You can mail me. I am writing my mail ID here.
Oh, thank you.
MP20003 @